Okay, it's up. All right, so let me now continue on from our first lecture, right? So we will do a quick review. So when we talk about lecture one, we talk about basically the motivation behind why architecture, right? And if you look deeper, basically, you're talking about this computer where you have the processing elements, right? The memory part, which acts like a scratch pad, and the I/O. And the I/O is where you store all the files, where you take all the inputs, the keyboard, where you display all the outputs. And then those things communicate with the main memory, and the main memory communicate with the CPU, right? And we talk about the age of Moore's law, which essentially kind of dictate, no, not dictate, but observe, right, that the amount of transistor increases. It used to be double every couple of years. What you're looking at is it does increase over time. It's almost linear, which means that you can dedicate more transistor to the fancy logic that we're gonna learn for the remainder of this class. All those tricks and things that we added to the CPU just to make it run faster, right? So we talk about what happened when we run this one program, which is really simple. It does get compiled, sent to the runtime. The runtime actually copy a portion, basically copy the code, right, to the main memory so that you can run the program. The computer knows where the program starts and run it. And that communicate with the ISA, which we're gonna learn today. What the heck is an ISA? You might have heard about assembly, right? Are both of you familiar with assembly? Not familiar as in like, have you heard about it? Have you seen it?
Yes, I have studied in my microcontrollers course before.
Okay, cool. So basically, those are the assembly that you have seen before. Today, we'll talk about how do we design one. What are the elements of coming up with, say, a new ISA? Or what are the requirements? What do I need, right? What are the needs and what are the good things to have? And what are the trade-offs? Once we have the ISA, we'll transition to now we have the interface to talk to the hardware. Now we would implement those hardware and actually talk about the trade-off between certain optimization, that the choices that you have and what you can do to make your computer faster for the user based on the transistor that you have on your chip, right? And we talk about one Neumann, which is sequential. The way you run the program is sequentially done. N plus 1, N plus 2, N plus 3 versus data flow, where you look at each operation and look at what's the data input that you require, and you run the operation only if you have all the inputs. Once you have all the inputs, you can fire it off and run, right? So the one that's more natural as a programmer, obviously, is the sequential program, right? You can kind of tell the computer what to do step by step. That's a lot easier, right? That's why Python is easier to use, to be honest, to most programmer than functional programming. So if you play around with this thing called functional programming before, like Haskell, Scala, or standard ML, you might have realized this thing can be annoying to program, and at least that's my experience, right? Because they cannot imitate what data flow is doing, and it maps well with the data flow model because you're gonna get a lot of performance. But it's more natural to use a sequential model for your ISA. In this class, in this course, we will learn how your hardware, your CPU that you buy, convert sequential instruction processing to data flow inside the hardware. Why do we need that? To get the best of both worlds. Programmer has a simple time coding, and then the hardware optimize your code into data flow automatically without the programmer even realizing, to make your code faster. right? So this is done to make sure your code, your sequential code is faster. And we end with, okay, what does this do? So if you break it down, the left side and the right side. So let me move to my pen. This is basically just a counter. What it counts is how many times you have to do the loop on the right side. It stop when the loop on the right side is over. When it's over is when A and B, whenever A equals B, that's it. D side will count, not counting, but it would do the difference between the bits of A and B. So let's say A is 1101 and B is 1011. When you do A XOR B, this is gone. This is gone. So because A XOR B, those become 0, you're gonna have 0110 out of A XOR B, right? And then the rest of this, what it does is it counts how many are the ones that are remaining from A XOR B. What it's actually doing, that's a terminology for this particular operation. It's called Hamming distance. The way Hamming distance works is basically how many bit flip that I have to do to make A equals B. How many bit flips switch from 1 to 0 or 0 to 1 to make sure I can change A into B. It does have uses in security. Basically, you can use this Hamming distance to check, first of all, if your bit flip, or if someone do something with the data bits that you see, right? So you can see you can use data flow program to encode something like this, right? And it allows you to do the counting part and the calculating the bits part separately in parallel, right? And that's basically the recap of the first lecture. Now we will talk about the content that I want to cover, which is the ISA and the microarchitecture. So if you take a class similar to this before, this will be kind of like a recap for you. If you're still curious about certain things, feel free to ask me. If I'm going too slow, also let me know, because Muhammad, basically, you told me you took this class, something like this before. If I'm going too slow, let me know. Opad, you took this class before, so I would assume that you know this, right? This is a review for you. By the way, hint, it's the same slide that you seen last year. So how can we talk to a computer? Basically, the way you talk to a computer is this. The only thing computer understand is our command in the zeros and one format, right? If you think about it, you break it down to the most simplistic level, it's just a voltage, high voltage, low voltage, right? That's what the computer understands. But the thing is, we have to figure out how to communicate with just low and high voltage. How many of you are familiar with Morse code?
Yes, I'm familiar with that.
Can I communicate with Morse code?
Yes.
So what does Morse code consist of?
I think zeros and ones only means high and low.
Yeah. If you look at Morse code, right, you have the short and the long signal, right? Essentially short and long signal. Think of it this way. Comparing this to Morse code, one of the, you just take short signal, maybe it's a 0, long signal is a 1. Now you can communicate, right? The same way. So that's how you can encrypt, right, 0 and 1s into an actual communication method that allows you to expand the character. Because now with Morse code, you can expand to 26 characters, the alphabets, right? In computer, you just need to expand it to whatever number you want, whatever character you want, whatever symbol that you want, whatever programs that you want, whatever data format that you want, because you have unlimited number of ones and zeros, right? So that's why binary format is kind of nice, because at the end of the day, it's simple to read. I just need to measure, hey, what's the voltage? Is it 0 or is it non-zero? If it's non-zero, that's a 1. If it's 0, that's a 0, right? In some computer, they flip that. If it's non-zero, that's a 0. If it's 0, that's a 1, depending on their design. But at the end of the day, it's just high and low voltage. So let's do this. The idea is, hey, if we want to talk to a computer and we know computer know how to measure the voltage, it means that I can just talk to a computer by representing our human language and human instruction that say add, multiply into binary format, right? That's our next task, because if we know we can communicate in binary, we just need to know computer know what does each set of binary mean. It's like Morse code that if you say, well, I don't know Morse code, sorry, but let's say letter A is like dash and dot, dot, dot. If you see dash and dot, 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 it means that it's a letter A. So the same thing. If the computer sees certain pattern, it means we are doing an add. For a different pattern, we are doing a multiply, and then we'll expand onto that. And it's like, what do I add it with? Where do I store the results? And expand on that to actually create our assembly language, right? So we can use this as an interface between assembly code and the computer. Now we have a way to talk to a computer. Now we have a way to allow the program that you write talk to the computer. It's not about talking to the computer through the program in Python, in C, in Java, but now you're talking with the computer through the whole stack, from the Python and Java and C code that you have, down to assembly, now down to microarchitecture. Now you can actually send the command. So now I want to clear up the difference. I'll promise you that this will be the first question on our midterm. What's the difference between the ISA and microarchitecture, right? So the difference is this. The instruction set architecture, or the ISA, is just a list of commands in the manual. So if you look at x86 ISA, right, if you search it in Google, you're gonna be able to browse to the Intel and AMD website that describe what does each of the assembly do, and how does Intel govern how to run the computer. From the software point of view, how do I use each of the command? How do I build the OS, Linux and Windows, to make sure it runs Intel chip? It would have a long detail on every single aspect of how to control the chip. It's a list of commands that the microarchitecture understands. The microarchitecture is the hardware, essentially that's it. It's the hardware that allows the computer circuit to perform each of the commands. So when you buy a microprocessor or your CPU or any integrated circuit that are programmable with an ISA, it's just a component that combines the ISA and the microarchitecture. For example, if you buy the Raspberry Pi, it would use the ARM ISA, right, to run that hardware. Inside the hardware itself is a microcontroller. It has multiple components to make sure it runs, and it runs fast. And it actually, in the Raspberry Pi case, doesn't use a lot of energy. So you have a server-grade computer, x86 ISA or IBM power. It runs also really fast, and it might support more parallel operations, and it consumes quite a lot of power, but it's energy efficient as well, right? The thing of ISA as a the interface between the software that you write and the circuits. So we are kind of breaking into the hardware world by now knowing how to control the circuit, right? So what are in the ISA? First of all, you'd have to have the instruction, right? You have to command the computer. Inside the instruction, there will be things we're gonna expand into this. So don't worry, this is like a high-level overview slide. So we're gonna have the opcode or the code for the operation. It basically is a fraction of the bits that represent what the heck are we doing? Is it an add? Is it a jump? Is this a branch? Is this a load and store, getting data from the main memory? The addressing mode and the data type, we expand into this in a bit. It would have instruction type and the format. It would actually tell, okay, this is a compute instruction. This is a memory instruction. This is a jump or branch instruction. And what are the formats? Are we looking at these bits to represent ones and zero? It would have the specification for the register and the condition code. So Muhammad, are you familiar with register?
Yes.
Okay, so I'm gonna skip over this a little bit. Register is a really, really fast temporally variable that is on your CPU. And the condition code is basically the result of the previous instruction. It will get updated whenever things like the result of the previous instruction have a carry bit or turns into 0. So the condition code that represent those things happening would be flipped to between 1 and 0. So 1 means true, 0 means false. Memory, there'll be address space bit, addressability bit, alignment bit. We'll talk about this in detail in a bit. And then the virtual memory management, we'll talk about this after the midterm. Virtual memory is a huge topic, which I kind of want to expand upon. And if you have questions, definitely check with me because I wanna. This is the area that I work in a lot, and this kind of dictate how to make sure each program doesn't really like peek into another program's data. It provides memory protection. It provides things like the notion of almost unlimited memory, so that the program doesn't crash when it tries to ask for too much memory. What else? It also dictates the calls, interrupt, exception handling. So if you're taking embedded system class, you're going to have to deal with the system call. Most embedded system class have to deal with system call. I'm not sure about this particular class at TGGS. I think you have to do I/O, right? You have to deal with the input and output signals. So you have to handle, what do I do? Now I read something. The I/O port reads something. It interrupts the microprocessor. So I need to actually handle that. The ISA will let you know how to handle that. Also have the access control, making sure you cannot read certain region because the data should be protected. It also should provide correct priority and privilege. Normal program, for example, should not be able to read or write into certain regions because this owned by Linux or is owned by Windows. You can't just do that. It has to have a way to interface with the I/O, which include things like keyboard input, mouse input, monitor output, things like the network packet coming in, dealing with the disk. So everything that I just explained are the I/O component. Also threat management, right? The ISA would determine and list out how do you manage the threat and how do you manage multi-threading. It also have things like power and thermal management. How can I lower the power to make sure I consume less amount of battery per second, right? And here's a microarchitecture. So now that we have the ISA that define what the software can do, right? You have the ISA that defines what the software can do. The microarchitecture simply implement these commands, right? Basically, it's a hardware that implement these commands with a design trade-off. Because basically, we built the hardware, we have to have the design trade-off to dictate this is what we desire. So we're gonna make sure we optimize for certain aspect of the design. How do we design this? It's kind of based on the program that you're running, right? And these are transparent to software. So we're gonna learn most things here, except for the last two. I think the last two is in the advanced class, which is next semester. But these are transparent to software. Things like pipelining in order versus outer order processor, right? The programmer doesn't know about this, but the CPU does this. So let's talk about some of the sample of this trade-off, right? The bit pattern for a floating point multiply, right? If you have 32 bits, you basically make a trade-off between accuracy. How many bits are you going to use to represent certain number for floating point? Have you heard about TF32? So the TF32 is called TensorFloat 32, which doesn't even use 32 bits. This is like a NVIDIA PR stunt that claimed that TF32 covered the same range as floating point 32 without using 32 bits. It actually used even less bit, so it consumed less energy, and you have more chance to kind of pack those bits up and process multiple instructions in parallel. What you lose is you lose accuracy. So if you use TF32 for something that demand accuracy, you might actually kill someone because of your error that generated from using TF32, right? So you need to know what are the trade-offs. Number of register in an x86 versus ARM ISA is different, right? It depends on the demand from the user and the way you define the ISA. Each one of these ISA would have different number of register, and the hardware will implement that specification. Number of ports. So what are ports in real life? What does port do?
It is used to actually communicate with some external device.
Yeah, so you're talking about like in terms of communication and computing, right? But in general, when you have a port, you allow chip to dock, right? And you transfer the good, right?
Yeah.
So that's what port do. So if I have one port versus two ports, what's the difference? I can basically transfer data between for one chip in parallel versus two chips in parallel, right? So the amount of port in the register files or the amount of port in the hardware components do the exact same thing. It's like how many of the same interface you're gonna have on the hardware pieces so that you can do this data transfer in parallel. The number of cycles to perform one multiply operation, right? So you can implement the multiply operation in many, many different ways. For example, adder, how to implement that and add in a hardware can be done in a different way. We are not going to go into the detail in this class, but these require different number of transistors, and it results in different performance for those adder and multiplier, right? The faster it is, more likely that you're going to have to use more transistor and more logic gates to implement them. So what happens if the ISA changes? One of the things you see is the assembly language doesn't change a lot. And if it changes, it should be backward compatible. Why is that the case? Think of it this way. If you switch the ISA, it means that every single program that compile for the old ISA will not run anymore. Anyone here owns the Apple M1 processor, new MacBook? So if you own that, you might not realize that some of the program need this Rosetta software that basically convert the ARM, well, the old x86 ISA into the ARM ISA for the M1 chip, right? So that's one thing that you can do. Because otherwise, you need to re-optimize your compiler for the new ISA and recompile every program for the new chip that use a different ISA. So alternate solution that Apple is doing is called code transformation. Basically, it's transform the binary of one ISA into another ISA so it runs. So this can be annoying, to be honest, if you have a lot of ISA. So in conclusion, if you don't want many of the ISAs, think of it as, okay, how many human language are there? And how many are prominent, right? The reason why we all communicate in English is because we don't really want to switch languages. It's annoying, right? So would it be a better world, like, to be honest, like if we have one language and everyone knows it? Do we have to struggle with like, okay, I can't speak German, so I need to learn German so that I can go to Germany, and then I have to speak English if I want to go to the US, and then I have to kind of know British English if I want to go to UK and understand what they're saying, right? So at the end of the day, when you design a computer, ISA would kind of converge into the dominant one, right? And think of it as a human language, but for software, right? They want to talk to the hardware, so the hardware should kind of operate in a few languages as possible. So these days you're talking about ARM ISA, x86 ISA. If you buy IBM supercomputer, you might see the Power ISA. And you might see things like RISC-V, which is coming up as well. RISC-V is what we call free and open, which is from academia, right? It's one of the research team that came up with this ISA to say, hey, this is a pretty good ISA design, and that is actually really good. It's extensible. It's pretty minimal but powerful, right? That doesn't have any string attached. So if you use x86, you kind of have to pay the guy who invented x86 64, which is AMD, a bit, right? If you want to build chips that use their ISA. For this RISC-V, you don't have to do that. It's all free because they want to make sure that we have new research into extending ISA and how to build chips that can be extended. How can we build new chips if we based on RISC-V? So what is the trade-off now that you have multiple ISA, right? First of all, the complexity of each instruction is one of the big trade-offs. What are you going to see for our lab? The MIPS R4000, which is the one that, as I said, the newer version of R4000 used in PlayStation and PlayStation 2. The MIPS ISA, you will see that it's a lot more simple than x86. So if you use RC in x86 before, if you have to look at assembly code in the Intel CPU before, it can be pretty complex. The MIPS R4000 is much more simple. So that's one of the major trade-offs, the complexity of each instruction. How instruction is specified, right? The assembly code would look different. The binary would look different. The pattern of ones and zero obviously would look different. It's like having multiple versions of Morse code, right? Let's say Morse code 1 and Morse code 2. If I somehow have two versions, version 1 and version 2, I need to make sure my recipient use the same version as I do. Otherwise, we'll miscommunicate. There's no way we can talk, right? Each ISA would have the different method to support each features. Some of them exist. Some of them just say, hey, we don't support these features, right? These features are either to enable more performance, enable lower power, right? So it depends on the goal of what do I want to achieve from my chip. The goal of what I want to achieve from my chip kind of dictates what the ISA has to support. So the type of ISA, so you might have heard about this. There was a lot of debate back like 50 years ago, actually more than 50 years ago now, whether you should use a complex, full-blown, super complete ISA. It's called complex ISA or CISC. This is a minimal version of the ISA. I know that my computer is Turing complete with my ISA, and that's it. I just want to do an add and load and store and branch, and that's all. It's capable of doing everything. We call this a reduced ISA or RISC, right? There are trade-offs between the two. And there's no definite answer which one is better and which one is worse. Because at the end of the day, to be honest, it involves multiple things. How you write the program, how to optimize the compiler, how to optimize the OS, right? The architecture, even the ISA is a small component of it. It's not even like the entire thing in architecture because we implement the hardware as well, right? So let's talk about the instruction now that we kind of transition into what is the ISA and we know what is the ISA now. Instruction is the most basic elements. between the software and the hardware. They want to talk to each other, right? So we need to use instruction to allow them to talk. What are the main components? Obviously, we need to have a way to tell what is the instruction we want to do. Is it an add? Is it a subtract? This is called the opcode. The opcode is telling what does the instruction do. The operand, basically think of it as an object, right? In English language, you have subject, verb, object. Verb is the opcode. Subject and object is the operand. Things that you're doing with and things that become the target, right, of your operation. So the operand is who are there that have to perform that instruction. So if you look at, let's say I have a dummy instruction called add R0, R1, and R2, which let me just define that. It means I'm gonna add R1 and R2 and write the result in R0. So this is my dummy instruction. I just created on the fly, right? The operator is the plus sign because I say it's add. R2, R1, and R0 are the operands. These are the object and the subject of my sentence, right? Think of it as a language. Just have an analogy as English language. It does have the structure. It does have the grammar. So those are the ISA. It dictates how we write English so that we can communicate. In this case, opcode is the verb. Operands is R0, R1, and R2. It tells me who is doing what, right? So that's the element of an ISA. So let's expand onto that. And I hate Microsoft PowerPoint because it's like to have this lingering pen when I transition. So the element of the ISA, first of all, it has to have the sequencing model. Control flow versus data flow. One Neumann versus data flow, basically. It has to have different processing styles, which means that how many operands do I put in per instruction? In the old machine, you can have zero addressing. So these are the addressing mode of the machine. Zero address means that I don't specify the operand. It's operand followed by just push and pop is a stack. We're not going to talk about it's too old. It's kind of not relevant. One address machine is what we call accumulator. I can count up and I can count down. I count up and count down. I count up this target. I count up the target. I count down the target. And then I load and store a target. The two address machine is the one that's more modern. So if you haven't, no, this is what x86 use. The Intel and AMD chip, they use the two address processing style. You have the operation followed by source and destination. Source means is where you take the value from. Destination means that that's where you write the value to after you're done. So let's say you want to do an add, and the register in x86, the name are things like EAX and ECX. So if you look at the Intel spec sheet, these are the register name. It's just a name of variable that we can use. And it will tell you what are those names. There's going to be a special name for that in Intel x86 and AMD chip. You do percent followed by the name, This is the source. This is the destination. What this do is basically you do destination equal, and these are the operation. Source, right? And then you do operation with the destination. This is how Intel assembly works. Destination equals source, operation, destination. So if it's an add, it means I'm going to add source and destination together and write it in the destination, right? That's a two address machine. So that's most of your CPU you use these days. The three address machine, I believe ARM is also three address, but I might be wrong. I might be wrong here. But the three address machine is more convenient because you have source 1 and source 2 and destination. So this basically means you do def equal source 1 up source 2. You do operation on source 1 and source 2 and write it in the destination. So this is more convenient because you kind of like, okay, I have both sources. I don't have to play around with destination becoming my source, right? But it's a little bit also, I need to specify 3 things rather than 2 things. So in terms of how packed your code can be, it can be trade-off. Your code can be shorter in here, but instruction might be longer because you have to specify more bits for source 1 and source 2. So what are the trade-off now that we talk about the trade-off, right? Space. How many bits do you need to represent your instruction? Why is that important? Let's say if you have to work with embedded processor, how much memory do you got? So if you take embedded system before on your lab, right? Do you have a rough idea about how much memory do you have for your microprocessor? So typically it can be like kilobytes or a few megabytes, right? Which means that you somehow have to write code that fit within the main memory. So your instruction should be short so that it fits. Otherwise, your instruction, if it's 32 bits or 64 bits per instruction, it's gonna overblow the memory. So you can't run anything, right? Number of executed operation that impact performance. So the 2-address machine, you're gonna likely to have ended up with more operation than 3-address machine because you have to juggle around with source and destination, right? So this is one of the elements of the ISA. What else? As I said, you have opcode, operand, and then the addressing mode, what we call operand specifier, right? Data type kind of dictates what does the bit represent. Is it an integer? Is that a floating point? Is that a character? Is it a binary? Is that a decimal number, right? These allows you to handle different data type. Even it might be able to handle things like an array or more complex structure like in the CIS ISA, such as x86 and WAX. So these are the 2 ISAs kind of well known that they are CIS processor. It supports so many different things. So there are ways to support more fancy, complex structure for different data. It's not just going to support integer and floating point and binary or character anymore. It supports more and more things. You also have the complexity of instruction, which means that can I just do an add and multiply? Or do I have an instruction that says load an entire array into my memory? With one instruction, I have done this, loading the whole thing to the main memory. Some of them in the CIS ISA, the complex ISA, will have this pre-built that even in X ISA, where it's called rep movef. Move is when you load the data. Rep movef is repeat loading. It's kind of like loading the entire array or loop around and load data together in one instruction, right? This is one of the examples of how CIS ISA make your life, it can make your life more convenient because it does have these fancy instructions. It also makes your life annoying because you have to implement the hardware for this instruction. You can have simple instruction like add, XOR, load, and store. That's all. Right? That's all. And it would make computer run. You can write a program that do complex instruction, right, in software by using this simple instruction. So that's the trade-off. Do I just go by with one instruction and I'm done? Or do I go with simple instruction, simple hardware so I can dedicate transistor for something else? It's not like your chip can, it can be even smaller for embedded processor, and I can make my chip the same size, but I have more transistor for fancy things that make my computer faster, right? With the risk reduced instruction instruction set architecture. So if you see here, basically the complex instruction can be built from a bunch of simple instructions. So that's the trade-off, right? With a complex ISA or CIS ISA, you have denser encoding, which means you can have a smaller code. it might work well if you want to pack the code as small as possible. And this kind of helps the compiler a little bit because there's always one instruction for everything. So it doesn't have to map a lot of instructions that are small together to perform one complex task. There's always instruction for that. For the reduced ISA, simplify the hardware. And then it allow more room for the compiler to optimize your code because it basically kind of mapped to the RISC ISA, simple instruction add, multiply, shift, XOR, right? So it allows more opportunity for the compiler to optimize your code. And these days and age, these are actually good because compiler can do a lot of things. If you're not familiar with what is a compiler and what are they capable of, basically compiler analyze your program and they convert your program into assembly. But it's not just doing the conversion. The conversion is a must. They have to make sure they convert your program into binary, but the compiler also optimize your assembly code for you so that it actually runs faster magically. Compiler is one of the really, really big field in computer science. It's like computer architecture. It's one of the big field in computer science and computer engineering because it actually dictates how does the compiler optimize your code, how does the compiler deal with certain languages so that you can make a code that's faster, more energy efficient, and more, I guess, more programmable, to be honest. Easier to program. How does the compiler handle things like Python, right? So these are big topics in compiler. And then I need to talk about this thing called semantic gap, right? It's the gap between the software and the ISA. So I can have something like a ISA with a large semantic gap, right? So instruction is just control set of signal in hardware. It doesn't really support much. And then the compiler needs to generate those control signal. So if you throw this at in the world, you probably get murdered by compiler people because there's too much of them. A small semantic gap would mean ISA almost look like a high-level language like Python, C, or Java, right? These allow more application-specific hardware optimization, which kind of means that instead of the ISA controlling each of the wires and transistor, which is can be a bad idea, right? Now you have each instruction that do a full-blown function calls in Python and things like that, which is also not a good idea. It's too much, right? We need to somehow implement all these things. And transition from one ISA to another ISA basically is kind of change the semantic gap. The ARM ISA will be at certain level. The ISA for x86 will be on another level, and you change the semantic gaps. And this can be done either in hardware or in software. There's also trade-off. So today we talk about multiple trade-offs. There's also trade-off with data types, right? What's the benefit of high-level data type? High-level data type are things like, I want a set, I want a map, right? Things that are kind of pre-built for you. A set or a map rather than an integer data that consisting of pointer and integer, which is a linked list, right? Or a graph. What's the downside of this? Basically, it also have to do with semantic gaps as well. Data type are tied to semantic level. So if you have a pre-built data type for a graph or a linked list or a tree, it means that your program can utilize them right away without you having to write code for that. It's more convenient, right? You don't have to write the implementation of a linked list in C or implementation of a queue in C. You can use it right away from the ISA. Somehow it's there for you. But we don't do that a lot because it's kind of getting rid of the benefit of more like a modular chip, modular ISA. You somehow need to implement everything here, which is a lot. So now we talk about data type, we talk about complexity of the operation. Let's move on to what are the elements of the ISA? What are the other things that are related more to the main memory? So we talk about the ISA would have the section on how does it deal with the memory on DRAM. It would have a section in a specification. It has to tell about what is address space. Address space is essentially how many unique locations that you can have in the main memory. That might be a location specific to a part of the program, specific to a part of shared data from multiple programs or shared library that each program would call in the API call. It might have a specification on how many processes can be run together at once. These address space would dictate that. It would dictate that, and it will tell you how do you manage it. What are the different range inside your memory that can be used for certain things. It will also have addressability. How much does each location store? Is it per byte, per bit? Right? I can go to each individual bits. 64 bit versus 32 bits, right? So these are the things that ISA would tell you. Can I go to each individual byte? Which is convenient, right? But it means you have to build the hardware to read each byte rather than each one block of 32 bit or 64 bits. So it's simplicity of the implementation versus you have to write a program to handle different things. So a quick exercise to show this trade-off is, if you want to see how complex things can be, if you support only one addressability, is what if you want to add two number, but it's 32-bit, and your ISA only support byte addressability, versus having to add 8-bit number, but your ISA only support 32-bit addressability. So you can imagine this can be annoying, right? Because the first case, you add 32-bit number in the byte addressability, which means you have to add each byte individually, which also means you have to handle this carry bit, right? If you have the carry bit from the earlier bytes, make sure you add 1 to the other bit. The second case, you want 8-bit number, but you have 32-bit addressability. So it means that you need to mask off. You read the whole 32-bit, then you need to figure out, okay, which one of the 8-bit do I have to do operation on, and marks it off. Then you add the number and write it back in the 32-bit addressability. So what happened here is you might figure out, this is annoying, right? This can be annoying. So most ISA that you have nowadays would support multiple of these addressability. There'll be an add for 32-bit. There'll be another add operation for 8-bit, add byte, or add word. The word means the data word that we specify in the ISA. This can be 32 or 64 bits. So this allows you to kind of like use individual addressability to do certain things. Why is that good? So if you're dealing with character char in C, like C language, you have the 1 byte character. If you want to add them together, you probably want to use byte addressability. Otherwise, you have to like do a lot of masking and adding. But if you want to add an integer, which are 4 bytes, then just use add word, right? So it kind of gives you the trade-off when you have to convert operation for certain data into different addressability. It also tell the virtual memory support, which we're not going to talk about it. Also would specify the big versus little endian. Big versus little endian basically dictate, if I look at a data word, which are 4 bytes, 4 bytes. And I said these words start at address, let's say address 10, 0x10, right? Which one is the address 10, 11, 12, and 13? So big versus little endian would dictate which one is the block for address 10, which one is the block for address 11. What else? It also would specify the number of register and how to access the register. Register. Register are just really, really fast, one cycle, really fast, temporary memory. it would tell you how many do we have and what's the size of each register. The benefit is these are really, really fast. Compare that to a cache on the main memory. These are way faster, a lot faster. It's used for you to actually process any data in the CPU. Any frequently used data will be stored in the register. Right? It is to take advantage of data locality. We'll talk about this when you talk about caching. So we're not going to go into the detail now. What does data locality mean? But it generally, it means that, okay, when do you use it a lot? You're going to put it in register because you know you're going to use it a lot. And there's also evolution register, which I want to put in a historical context, because back in the day, you only have things like I can add up, count down. These are called accumulator. So these are simple, really simple to design, but annoying to use, right? Because they're annoying, once we have advances in circuits and digital circuits, we can use things like accumulator plus a way to specify the address, tell where in the memory we want to access. So that's the next evolution. And then the last evolution, which we use right now, is every register act like a temporary variable. We call this general purpose register. Our register can be used for all purposes. It is easy to use, easy to manipulate. It ranges from a few register to a lot, like Intel Itanium processor, which is the one that Intel used to have, and it doesn't really sell anymore because it kind of morphed into the x86 64, which is the AMD take on x86 64-bit version. But Intel's take on 64-bit version back in the day was like, okay, let's add 128 register. Because they know in a server, there's likely that they might use more register, right? So it also does provide trade-off. You have more register, but you have to build the hardware for them. You have to actually build those registers inside the CPU, right? What else? The elements of the ISA include things like addressing mode, how to obtain the operand. For example, you can have absolute addressing mode. Things like if I do load R0 and number 10, it means that I'm going to go to address 10, like the actual value 10 in DRAM. That address, put whatever data are there into R0, right? So the value at address 10 will be put on R0. So you can have absolute number. Just take that number as an address. You can have register indirect, which basically means that you have this parenthesis inside the register name. It is the same as, let's look at R1. And whatever data R1 is, that becomes the address. So you load the value at address R1 into R0. So this is called register indirect. The reason why we call this is you look at the register value, that becomes the indirection for the address. It can be displaced or base, which is load R0 offset R1. It means that I start with the value of R1, same as register indirect, but I don't want to load that data. I want to load that data plus 10 or plus something. So over here, you load offset plus this value into R0, right? So the more you support, the more convenient it gets for the ISA and the software programmer, because I can use multiple ways to access my data. And to be honest, modern ISA support multiple versions of this, so that you can specify and load data in a different way. There'll be multiple versions of the load command or the store command to take advantage of different formats that you can use, and you should use the one that's fastest. If you have to write assembly code. In this class, we're not going to ask you to write assembly code, by the way. And each ISA would have a definition of how do you use addressing mode. So these are just examples. In the ISA manual, it would tell you how do you use it. It would specifically, if you do load R0 10, this is what it means. You have to confirm that with the manual, because Once you become the hardware architect, you design that manual. So you can design in any way you want, right? As long as it's functional, you can put whatever weird ISA we have. And one example that we'll show you is like on the midterm, there'll be a question on, I just came up with my own ISA, write code in that ISA. How do I represent certain instruction in that ISA, right? So what are the trade-offs, right? With more addressing mode, you reduce number of instruction because you can use different versions to do different things. Some access are better suited for certain mode. For example, if you have array access, right? How many of you have code like this? For I equals 0, I is less than n, I plus plus, and then you do a of I equals 0. It's super common, right? What it does is basically you start from a of 0. A of 0 would be your register value, and then you plus 4 every time you have to load the data because it's 4 bytes for integer. Let's say A is an integer array, right? So you would do offset of 0 plus so basically the way you convert this to assembly, it might be something like this. 0 plus R1, and let's say R1 is A0, right? And then the next instruction will be load. No, store. This is storing. So 4 plus R1, and then 8 plus R1, and then 12. Oops, sorry, 12 plus R1, right? So this is basically one way you can keep loading this value with this particular addressing mode, which is convenient for these purposes. Pointer chasing, it might be different. Pointer chasing is things like linked list. So you want to use register indirect, right? Because your pointer becomes the register value and you load it from there. Sparse data would use a different mode as well. You might want to use just absolute address because your data is everywhere in DRAM. There's no way you can specify the offset based on register. What is the downside? Oh, more work for a compiler. You need to build complex compiler to translate program into different addressing mode. But this also means more performance. This also means more performance. When you said more work, when I said more work for the compiler, it basically kind of means that when you compile the code, it's likely to take more time. It's likely to take more time to compile your code, but you ended up with a program that's faster. Right? So generally, this is good. And more work for the microarchitect because we need to build the hardware to support all this addressing mode. But again, most of the time, this trade-off is good because we give you the option to use different things to make your program faster, right? Okay, so that's the trade-off for each addressing mode. What else? The ISA would have to specify how do we interface with the I/O. There's going to be a region of memory that is called memory map I/O. You map the input and output data to the region in the memory. So the program knows that, okay, if I read from this address, it means that it's the data coming in from, say, your network or your disk or the other I/O. If I store data to this region, it means that it's going to the monitor. It might be the pixel value that goes to your monitor and things like that. You can have special I/O instruction that deal with each of the input and output devices, like your mouse and keyboard, right? Call this instruction when someone hit Control Alternate Delete, right? Because you want to interrupt and show that task manager in the Windows and things like that. You have the another element is privilege versus like user versus supervisor. Supervisor is like when you are Linux and Windows. Right? So you need to control a lot of things versus when you're just an application running like PowerPoint, Microsoft Word, you don't need access to the data that Windows holds, right? So the ISA need to figure out how do I protect those data, and it tells who can execute what, right? Who can execute what, which is kind of like one of the basic of like how we can have the antivirus software to prevent this software from running certain things. You have in the ISA would have the specification for exception and interrupt handling. So we'll talk about what are exception and interrupts in lecture, I think 6. It's basically a procedure to follow when something either go wrong or something happen. Like I typed on the keyboard. When I type on the keyboard, it means I'm interrupting the computer. So the computer has to come in and take those commands and do something for me, right? The ISA would specify how do I call the function based on when certain thing happen. Or even when you say turn off your computer, when you hit the power button, that's also another interrupt. It's an interrupt to say turn off the computer. The computer would say, okay, I have to do this routine to power off, right? It can be vector or non-vector interrupts. So these are the way the ISA would implement how do we handle these interrupts, and it change over. x86 would do it one way, ARM would do it in a different way. If you're curious, feel free to Google that. And if you still have questions about what the heck is vector versus non-vector interrupts, feel free to let me know. But I think this should be covered in the embedded system class. You also have to specify how virtual memory is managed, how to protect the data from one program, from reading the data from another program. So it has access protection. All right. So now that we talk about the elements of the ISA, let's see. I'm trying to figure out when should we take. Oh, okay, almost. So we are almost done with the first half of the class. So bear with me. I just need to talk about a few more things. So the next thing is the class of instructions. So you have the compute instruction. It operate on data, right? So these are compute instruction. It process data, take operands, compute results, write the result. You have data movement. Data movement means I'm going to the memory to take the data in, or I write something to the main memory. So it moves data between each component. So that's called data movement. So that's the second class. The last class is called control flow instruction. What it does is it change the sequence of how you run the instruction. What are these? If else. So when you have if else or for loop, you jump between your code, right? So the register involved in this is only for the program counter. And we will talk about the program counter in the second half of the class, of today's class, what it does and how do you process the instruction. But the program counter, think about it, it's a pointer, it's a register that point to the current line you're running. That's how you can keep track of where you are when you run the program, right? The program counter would point to where you're running. So when you have control flow instruction, you jump by changing the value of program counter to the location of where you want to jump to. You can have the load store architecture versus the memory to memory architecture. Load store architecture means that whenever I want to interact to the main memory, I need to get that, bring it to the CPU, and write it back to the main memory. That's a load store architecture. Instruction have the operand only to the register. So you need to first load the data to the register and do something with it, and then store the data back to the main memory, right? So these are the key. Memory to memory register, in many sys ISA, they extend this assumption and say, hey, if I want to just copy, let's say if I want to do this, A of I equal B of I, right? Why do I even need to load them to the register? Because I know it's one memory location to another memory location, right? So you can have memory to memory architecture, which support this kind of thing as well. So what are the trade-offs? Performance, obviously, because you have to somehow bring the data back and forth, right? But complexity as well, because somehow you have to control that in the main memory, right? The next trade-off is instruction length. So you can have a simple ISA with a fixed length. Every instruction is 32 bits. Every instruction is 64 bits, right? This is simple because it's easier to decode. Okay, it's always I need to remember to change this this presentation because I always have this typo. It's easier to decode. It's easier to figure out what is this instruction. Because I know that this instruction is definitely this many bytes. It's easier to decode multiple instructions at the same time. Because I know exactly, if I know the instruction is 32 bytes, I mean 32 bits, 4 bytes. If I know instruction is 32 bit or 4 bytes or 64 bit, 8 bytes, it means that I can locate the next instruction right away, right? And what byte is that? Let's say right now I'm at byte 10 and I know instruction is 4 bytes. I know the next instruction is byte 14. I also know the next instruction is going to be byte 18, right? Because I know the length. So I can take them all in and process everything in parallel. So it's easier to do that. But it can waste bits, right? Because let's say if I have an instruction that only need 10 bits, but I have a ISA that say every single instruction has to take 32 bits. It means that you're wasting these 22 bits without using anything, right? And it can be harder to extend because at the end of the day, at some point you will run out. If you say it's 32 bit in length, it means that you only have 2 to the 32 different options to specify your instruction, right? So you can run out. And this is one of the examples. RISC-V is a fixed length ISA. You can see that there's a 32-bit format and 16-bit format. And you can see the opcode will be located here from bit 0 to bit 6. So that's total 7 bits, right? So you have 2 to the 7 different operations you can support. And you can kind of extend that a little bit using this bit 14 and 12. 3 more bits. And then a few more bits right here. If you want to kind of extend even further, depending on how you want to construct the instruction, right? So you can see that these are not as easy to extend if you have the fixed lengths, but it's possible. And it's easy to process things in parallel because you can say, hey, I'm going to get the first 4 instructions. I know where exactly do I locate them. You can have variable lengths, which would allow your code to be smaller because you only need the length just for that instruction. Just for that instruction. But it's harder to decode because you cannot tell how long is your instruction. And one good example of these ISA is the x86 Intel and AMD has the variable length instruction. For example, if you look at the manual, you can find that there are, for this VEX instruction, there are the 3-byte version and 2-byte version. If you read, if the first byte read 11000100, it's the 3-byte version, so you need to get 2 more bytes to process them. If you somehow read 11000101, it means that it's a 2-byte version, so you just get 1 more byte and process them. What does this mean? It means that you can kind of need to peek into the first byte before you know how many more bytes you have to bring in, right? So these becomes more complex to process things in parallel. Even just to process one instruction, you need to read the first byte before you tell how much more are you going to have to fetch, right? So this can make your decoder logic more complex. And this becomes a trade-off, right? You can also have the decoding trade-off. Uniform decode means that the same bit position, the same position correspond to the same thing. Let me go back a few slides and look at the RISC-V ISA. Look at this part, right? This is uniform. The first 7 bits is always the opcode. So this is an example of uniform decode, right? So you know, if you look at those bits, it's gonna be the operation bit. So just look at that and you know what you are doing. So that's a uniform decode. It allows more parallelism because you know exactly what bit representing the operations, and it's easier to decode. But again, you can waste instruction space because you know for sure you need those bits. So if you somehow need only 4 bits, you're wasting the extra bits that are there for the operation bits. Non-uniform decode is more compact and it's easier to expand because I can just say, hey, this a few more bits become the opcode bit, but it's complex to decode the logic, right? So I have a quick in-class exercise, which I don't recommend you to do now. I'm gonna kind of expand our lab 1 to include this lab 1A part. This XSPIM is actually the MIPS simulator. It's the same ISA that we are asking you to work on for the lab. But this is a simulator that takes in your code in MIPS assembly and it runs and it shows what's happening. So go to this site. The manual is right here. The site that contains the program is right here. And write the following function for lab 1A. These are not gonna be great. So if you want to skip that completely, it's fine, but it does help with the learning for the actual lab 1. So this is not going to be graded because it's just part of the exercise. But it's good to try, at least to try a code that say add two numbers together, right? In the starter code, we have some starter code for you to, I guess the tester code for you to test your ISA and your simulator. But these are fully functional simulators, so it's actually another good resource to try to see what's happening when you run this code, right? So if you actually commit to trying this and you have questions, send me an email. I will troubleshoot that and help you through it. I do have a video on my YouTube actually on how to use this simulator. I will share the link in the announcement, so you can just watch the video and see how do I go through the simulator and see if how do I run them. All right. So now we are transitioning to the hardware side of things. So hopefully this will be less of the just me telling you things and more of the, okay, this is what happened. This is what happened in the hardware. Let's take a quick break because there's already a lot of material. So let's do a 10 minutes, no, 12 minutes break. We'll meet again at 10:45. Is that okay? So I'm gonna get some water. I'll be right back at 10:40, and we'll have 5 minutes of Q&A if you have questions. If you don't have questions, we'll spend those 5 minutes just taking a break so that you can kind of process what we've been covering so far. It's a lot of material, all right? Okay, so that's all. I'm gonna stop the video and I'll shut up so you can take a break. All right, we'll meet again I'll be back at 10:40. If you have questions, we'll meet again at 10:45. All right. Okay, cool. All right, I'm back in case anyone have any questions. Otherwise, I'm just gonna take a quick break until it's 10:45.
Sir, I do have a question from the assignment. Uh,
Yeah.
Sir, you have used double pointers in that assignment.
Wait. Your voice is breaking up a little bit. Can you
Let's
say it? Yeah.
turn off fan. Yeah, is it clear now, sir?
Yes. Perfect.
Okay, so you have used double pointers in the assignment in the template of the code given. So I searched for the double pointer, but I'm not pretty much clear how to use a double pointer. The task was to calculate the determinant of the matrix, and in the function you just put double pointer as an input to the function.
So those are the basically we can use pointer or pointer. So what is a pointer for in C?
To
You can
point
use it
to
to represent an array, right? So a pointer, you can think of it as it's an array of pointer, which means that they can be an array of array, which also means it's a 2D array. So that you can actually process the input data using that. So the inner pointer or the inner array would be maybe this the row elements, and each outer pointer would be you go one column by one column. So if you are not familiar with this, I think for the purpose of this class, it's okay. But for the purpose of being a normal engineer, you need to know what is like what does those do? Like otherwise it is like a default expectation. You need to be familiar with like using pointers and also just like basically array of pointer in general. So those are typical requirements that I recommend if you keep because lab 1 is already out. So this is what I'm going to recommend, right? Prioritize lab 1. But keep this in mind. If you have time, work on this particular problem to make sure that before you graduate, you know how to use array of array inside C. This is really, really, really crucial. So it's a good. It's not. I'm not gonna even call it a skill. It's a crucial default thing that you need to know before you graduate undergraduate degree. That in computer engineering or computer science, you need to know how to do this. So if you're not familiar with it, please do it now. It's gonna be a default expectation from most company that you should know how to do this. Especially, well, I understand that these day and age, people use Python a lot, people use Java a lot, but the concept of a pointer has to be, you have to have that concept, right? So play around with it. It's not hard. Basically, it's a 2D array. And it's a 2D dynamic array where, because it's a pointer, it can be dynamic, right? You can have any number of the Y elements and any number of the X elements. Yeah.
Yeah. Okay.
All right. So any other questions?
No, not
Okay.
from my side.
I will make sure for first of all, and also the double point, I think is there? I think that's it, right? That's the only one that has a double pointer. So treat it as because we are representing metrics, right? There are two ways to do this. You can have a long 1D pointer, and for performance sake, the one long 1D pointer might be faster depending on how you implement this. But the pointer, basically array of pointer is actually used in multiple application if you want to get the performance in C implementation of your code. Yeah. Okay, so awesome. So let's continue on for our class, right? And make sure we cover everything before we do another Q&A toward the end of this class. So I'm gonna transition into the concept called single cycle architecture. And this is basically the majority of the first lab, right? You are going to implement a simulator for a MIPS ISA that would be single cycle. Basically, everything is done in one cycle. So if you have the ISA is what the programmer can see, can interact, and can program, right? If you think about it, you can write assembly code, right? When you write assembly code, you have the ability to modify everything as long as they run, right? As long as it abide by the rule and as long as they run. These are the state, which is basically think of it as a status of everything, the value of everything when you take a snapshot of time, right? The state of the ISA that are visible to the programmer. These are called the architectural state. What are they? They are, for example, the ISA would cover things like the name of the register, the program counter, and the memory. So the value inside them are reachable. The programmer can read them, can modify them. Right? These are visible to the programmer. So the key takeaway here is the programmer has the ability to read it out, to modify them, right? These are visible to programmer. Then there are also many, many, many things, right, that are going on that are not visible to the programmer. These are things that are happening in hardware. These are things that are managed and happen in hardware, right? These are called microarchitectural state, right? And the key difference, as I said, is these are the hardware implementation that we do, and we don't expose it because it make your life as a programmer easier, because you don't have to worry about, okay, what's happening in that transistor, what's happening in that particular wires, how do I go and proceed through each step of adding two numbers or multiplying two numbers, right? There's no need for you as a programmer to worry about that. It's a little bit too much, right? So these are called the microarchitectural state. And there's no way for programmer to access this. And this is one of the majority of a lot of architecture work. Because of actually multiple reasons, but one of the main reasons is it makes your life as a programmer easier. It also makes the computer faster. In most cases. If it's not faster, it's going to consume less power, or it will make your chip smaller. There's going to be certain benefit to each of the design, right? And then the example of this is like, are you familiar with this word caching? So how many of you buy CPU before, like buy a processor before? So if you built your own computer before, one of the things that you have to select and buy, right, is the actual CPU. That's your brain of your computer, right? And if you look at your CPU specification, right, for each of the model, they're gonna have a different size of the cache. These are, think of it as these are tiny amount of memory that you can have that are faster than going to DRAM, go to the main memory, but they're still slower than the register. The value of things inside the cache is a microarchitectural state. The cache are being managed completely by the hardware. The hardware would manage the cache for you because it's gonna simplify, right? It will simplify your programmer life. You don't have to manage this. Unless you program in the GPU allow you to modify the cache. But you also have an option to don't do that. I'll let the hardware manage it. Things like what happened to the register in the middle of the adding operation. Let's say I'm adding to a number. What happened to the register in the middle? The hardware don't tell that. Right? The hardware just tell the result at the end. So these are states that are not visible to programming. So now that we have the ISA, we have the method, right? We have the method to talk to the computer. How about the hardware? Basically, we have to string together circuits. And in this class, again, don't get scared because I'm not going to talk. I'm not going to ask you to string together circuits. We are just writing the simulator so we know the high level concepts and we know how computer works. So when you graduate, you know exactly what's happening when you run certain things, right? But in the end, at the end of the day, the hardware would have to string together all this circuit together. And the machine would figure out, right? Okay, I got this instruction. This had to happen. I got an add instruction. I need to read two values and add them together and write the result back, right? So in the conceptual level, it basically means that you have this architectural state one. You have the instruction coming in. You have to process it, right? It's being processed. And after it's done, you get architectural state two. So we're going to keep this high-level model. You have the original state, process instruction, result in the next state. So what do we expect, right? The ISA would specify what does state 2 look like after I run the instruction and after I know what is state 1. Basically, it tells you, okay, if I do this, this would happen, and this would be the result. So what's missing is what's happening in the middle. Everything that's happening in the middle is protected so that programmer don't have to worry about that. So from the ISA and the programmer point of view, there's nothing in the middle. In reality, there's so many things that's happening in the middle to make your CPU fast. So these are the implementation of the hardware or the microarchitecture implementation on how do we get from AS1 to AS2. And that can be any number of intermediate steps in the middle because you have multiple design choices. Single cycle architecture, which is your lab one, nothing in the middle. You just go from AS1 to AS2 right away. It might take a long time to go from AS1 to AS2. That one step can take a long time, but we don't care. Just do that, right? In a more advanced processor, but I would say like this is like 40 years ago kind of processor, you can have multiple intermediate steps, a few like 3 or 4 or 5 steps or 6 steps in the middle to transition between AS1 to temporarily step 1, temporarily step 2, temporarily step 3 before you go to AS2. And this use multiple clock cycle. The trade-off here is the clock for the first bullet point, AS1 to AS2, that one clock cycle is going to take a long time, right? Because physically you are doing this whole task. But if you do AS1 and temp1, temp2, temp3, and then AS2, each clock cycle can be faster. This is how you can increase the clock cycle in your CPU. And in lecture number 3 and 4, we will talk about what's the advantage of this. In this lecture, let's assume we do everything in one cycle and show what happened, right? So let's talk a little bit about the background that I would like for you all to have. The first background is combinational logic. If you're familiar with it, awesome. If you're not familiar with it, it's just a string of AND or NOT XOR gates that together do certain things like add, multiply, subtract. That's all. That's what the combinational logic is. Right? Sequential logic, as the name suggests, is the logic gates that when you string together, things happen in sequence. There's an element of time into that. And the one that controls the time is the clock. Sequential logic enable the state that we see because you can stop the clock and look at this sequential logic and look at what's the data in there. For example, what's the data in the register file at this moment in time before I process the next instruction? Combinational logic, everything happened in one cycle. Everything happened in the same cycle. So that when you do an add, you get the result right away. And you store them in the sequential logic. Critical path is the think of it as the longest road for the electron to propagate from the source to the destination, because electron is a physical thing. Right? Electron is a physical thing. So if you think about it, what happened is, let's say you have a logic that something like this, right? These are AND and OR, right? And then you do a NOT, I guess, and then you AND with the I don't know, this input again, right? If you look at this logic, the one that's likely is the longest road between the source, right? The source 1, source 2, source 3 to the destination. Which one is the longest? It's probably the source 1 down to the destination, or source 2 down to the destination is the same length, right? So these are likely to be the critical path. Why are they important? You want to make sure that the value at, when you measure the data at here, and here, the data should be correct to make sure your circuit is correct, right? So you want to make sure your data is the correct value before you go to the next clock cycle. To make sure the data has the correct value, you need to allow the time for electron to propagate from the source to the destination. That time determines the clock. This determines how fast your CPU clock can be. Because what happens if you clock too fast? Let's say if I clock it too fast, what happens here is this thing might go wrong because I haven't had the time to actually make that last AND gate producing the result, right? So these dictate how fast your CPU can be. So is it clear? Okay, so now that we know this concept, let's talk about the simplest design of all, the single cycle processor. Let's compute every single thing in one clock cycle. We don't care about how long that clock would be. It's going to be long, but it's simple. So it's a good way to kind of learn how to build a processor. So you have architectural state 1, and you have combinational logic. You do something like add, multiply, load, and store, things like that, right? Then you got to architectural state 2, then you use sequential logic to store the state. You store the results, right? And repeat. That's it. So the critical part is at this point, right? It's the time it takes for me to guarantee that every single instruction finish whatever they have to do. That's the critical part. So what determines the critical part of the combinational logic, right? If you think about it, let's say you have 1,000 instructions that you have to support in your ISA, right? The critical part essentially is the slowest one, right? Let's say you are, there's no sports that does this, but let's say you want to run in laps in a sport event, right? And you have each team. And the requirement for a team to finish is everyone have to run 10 laps. And everyone in the team has to run 10 laps, right? So who is the critical path? Who is going to generate the critical path? It's going to be the slowest guy on your team, right? Because no one else cares about the fast guy, because at some point he'll reach the finish line, and the person who is the slowest would determine who wins. Same here as single cycle processor. You're gonna have the slowest instruction in your team or in your ISA that dictates how slow the clock has to be, right? That's why, first of all, it's simple, but it's bad. It's a bad initial design, and we'll improve on this gradually across the semester, right? But our first design is simple. So what if, and then this is basically why the thing can be slow. If you need to access DRAM, it's gonna take a lot of time. If you need to access the disk, it's gonna take even more time. This is like millisecond rather than microsecond, rather than nanosecond within the register access latency. And you probably don't want to end up with a 1 kilohertz processor, right? But let's study how this can be built for now. So how do we measure performance, right? How do we actually measure performance? The question here is, let's say you buy chip. Can you just look at the clock cycle and say, hey, this is better than the other CPU? It's a yes and no question, right? Let's say I have a single core 5 gigahertz processor, but only one core, versus another processor with 4 core, but 4 gigahertz. Now you cannot tell, right? It's harder to tell which one is better. So a few things that kind of dictate performance. So I leave the question out here to make you think that, hey, clock is one thing. It's definitely important. If I look at one core processor or 4 core processor even, but one of them has 4 gigahertz, the other one is 3.5 gigahertz, that's more likely that the 4 gigahertz one would be faster. But it's not everything, right? These day and age, if you want to measure performance, somehow you need to look at benchmarking results, like run real application and see how fast they are and things like that. So just be aware these are not everything. Just be aware these are not everything. And let's look at what happened in one cycle, right? So instruction basically are processed in steps. So recall the first lecture. Every program are in your main memory. When you run a program, the program binary code get copied to the main memory. So the steps are this. The first thing is you need to figure out, okay, what is this line that I need to run? The first thing I need to know is like, okay, what's the line of code that I'm running right now, right? In assembly. That's called fetching the instruction. You need to go to the memory, fetch the binary of that program, that line, so that you can decode, figure out what the instruction is doing. Then once you decode, you say, oh, okay, there's an add instruction. This bit pattern is an add instruction. Then you evaluate the address. Okay, do I add from this location with this location, put the results here? Do I add from this register to this register and put the results here? Then you fetch the operand. Now you know where is the source. So you go and get them. Basically, that's the next step. You go and get the source. After you have the data from source 1 and source 2, run it, right? Execute is an add, so add source 1 and source 2. It's a multiply source 1 and source 2. After you're done, store the result back. So these are the steps, right? Each instruction might take out the steps. Some instruction would take some of these steps. For example, if you just add R1 and R2 together, there's no need for you to get the data from the main memory. So there's no need to evaluate the address because you have the data ready in the register file, right? But generally, these are the steps. And when you compare single cycle versus multi-cycle processor, single cycle, everything is done in one step. Multi-cycle processor, which we will go into more detail next lecture, we will break down this step into multiple cycles, and each of the steps will take as many cycles to complete. Well, think of this. Let's say I want to execute, right? Let's say I want to execute, add would take less time than multiply. So if I break the step down into fetch, decode, trying to figure out what instruction is doing, then execute, right? It means that the execute stage, the slowest operation still will dictate right? But at least you now decouple the execute from working with the memory. So now it might be just as long as the multiply. And in the real design, you can even divide this further into like add 1, add 2, add 3, multiply 1, multiply 2, multiply 3, multiply 4, multiply 5, right? So you can make your clock even faster. And modern computers are built this way. The CPU that you have is built this way. It basically slices the steps into smaller steps so that you can do one step at a time, so that you can clock it really fast. And then we will learn about another technique called pipelining to make sure you can make it even faster. Right. So bear with me for now. This lecture, we will just talk about this, and we'll make your processor faster and faster and faster. Let's go back to one more basic, data path versus control logic. So when you process an instruction, right, what it means is you change from architectural step 1 to 2. At the same time, your data change, right? When you add two numbers together, your data change from D1 to D1 prime. Basically, that's how you compute things. So that's why computers are useful. You do one thing at a time. You convert the data so that eventually it becomes your output of the program. Think of it as a math function, essentially. These are done through what we call functional units. Somehow we call this processing element. Basically, this performs the operation on my data, right? An instruction would tell what the operation is. The steps when you have to process the instruction consists of two components. The data part are the hardware itself. The data part are the hardware itself. It deals with the hardware that do adding, multiplying, the storage, which is register, right? The wires, the mux that select what goes into the input. The control logic is the one that control your hardware. It's the one that control your hardware. All right. So let's go with a toy example of my processor, right? So the first thing is, let's assume I have the program counter. IR and PC are the same thing. These are the program counter. And let's say we just execute, let's say we just did line n-1. Let's say instruction is 4 bytes, right? So this is line n-4. The reason I do -4 is 4 bytes for each instruction. So let's say I just do instruction n-4. What happened is in this cycle, because I just did n-4, the next line in your assembly is n, right? One instruction is 4 bytes. So if I go byte by byte, the address of my next instruction is n. The address of my next instruction afterwards is n+4, and then n+8, and then n+12, right? So let's say I just did n-4, and I need to do line n right now. What I do is, this PC is now n-4. So what is n-4 plus 4? It's n, right? This is the line we want to fetch. We just did n-4. So if I put PC plus 4, I will get the line n. So there'll be a connection here, right? This takes in n. The value n goes in here. The value n goes in here as an address. Why address? Because in the main memory, let's say this is where your program is located. This is where your code is located. You just did this line. This is line n-4, right? Because you just run line n-4. In this cycle, you want to run line number n, because that's the next instruction. You increment the address so that you can read from line number n. All right. So let's assume that this instruction is 11110000 and blah blah blah. Basically, just complete that into 32 bits, right? Because I don't have room to write 32 bits here. Let's just assume things happen. That data, this actual instruction would be fetched into our decoder. Decoder then figure out, right? Decoder then figure out, okay, I see this instruction. I'm going to select something from a register file so that they get add or multiply or load or do whatever with the execute stage, right? Based on this actual instruction. Decoder would figure it out. So the big part about your lab, the lab 1, is all in here. I see this bit pattern, do this. I see this bit pattern, do this. I see this bit pattern, do this. That's all. It's a giant decoder. Is like a, if you think about it, it's a giant if-else switch case statement based on your bit pattern, trigger different thing. And if you have to access the memory, then put the address to the main memory so that you can read the data back. If not, then you have the result. Let's say you want to add two things. So add 0 plus R1. So over here, the data would be R0 plus R1, which then you can select what goes back to the register file, because now you're done with running the instruction. So you write the data back to either the register files, or if this is a jump instruction, basically it's a if else or for loop. Instead of writing back to the register file, you want to write it back to your program counter, because you actually can jump to a different part of your code. And that's all. Like that's all with the toy example. We'll go into more detail and use a sample real, well, not real, it's a toy ISA for this class, right? That I came up with. It's simple so that we can go through the simple example, right? So let's start with our toy ISA for this class. Let's say we are using a simple 16-bit ISA. Each instruction is 16 bits. And I have 8 registers in the register files, which means that if I want to represent register files, register 0 to register 7, I need 3 bits, right? 0, 0, 0 is R0. 0, 0, 1 would be R1. 1, 0, 1 in this case would be R5. 1, 1, 1 would be R7. With 3 bits, I have enough room to represent all register I have, right? And let's say I have 3 address machine, which means my instruction format would be source 1, source 2, destination. So let's say if I want to do an add, it would be something like this. Add R0, R1, and then R2, which would basically means that R2 equal R0 plus R1, right? With me so far. What else do we need? Obviously, we need the opcode bit. We need to know that's an add, that's a subtract, that's a multiply, right? We need to make sure that we have the bits that represent where's source 1, where's source 2, where's destination, right? And in case, let's say we want to add R0, 20, and R1, which basically means that R1 equals R0 plus 20, right? We need to make sure we have the bits for this immediate. We call this constant number immediate. So we need to make sure we have room for immediate bits too, right? And remember, this is our own ISA. Let's build this from ground up with nothing, just blank paper. So let's make this ISA and make sure it runs, right? We can do whatever we want. So let's do whatever we want. So let's say I have this toy ISA, and I will make this assumption. These are the bit pattern, bit 0 to bit 15, right? We have, again, 16 bits. Let's build our own ISA, right? Let's build our own ISA. Let's do the first type of instruction. Compute with source 1 and source 2 and write the result to destination. Because I know that 3 bits are for source 1, 3 bits are for source 2, and 3 bits are for destination, because register there are 8 registers, so I need 3 bits for source 1, source 2, and destination, right? So I can use the remaining empty bits for the opcode. So let's assume that. These are all assumptions. I can do whatever I want. Again, I can do whatever I want. I can say opcode will be 5 bits that I don't care about these 2 bits. That works too. But in this case, let me assume that I want these 2 more bits. in case I want to support more instruction for this particular compute with register. If I want to do something like add R0 and 20 into R1, then I can do this. I would say the bit 6 to 10 represent the immediate, right? What is the value 20 in binary? 20 is 16 plus 4, right? So that's essentially 0, 1, 0, 1, 0, 0, right? We have 5 bits. We have 5 bits here, so we strictly can have, if I want to represent 20 here, I would just put in 1, 0, 1, 0, 0. That's a number 20, right? If I put it here, what is R0? What do I put in for source 1 if I want that to be R0? I can put in 0, 0, 0, right? And R1, destination, I'll put in 0, 0, 1. I just need the bit to represent, oh, that's R0 and that's R1. And I just assume that R0 would take in 0, 0, 0, R1 would take in 0, 0, 1, R of n would be the bit that represents number n. Right? So in this case, if I want to do add R0, 20, R1, let's just make sure we haven't specified the add pattern yet, but the rest of the bit would be 1, 0, 1, 0, 0 for 20, 0, 0, 0 for R0, 0, 0, 1 for R1, right? And this is how you can specify you want to do add 20, R0, R1. And that's all, right? That's how you can construct an ISA. And you can do load, store immediate. Basically, you put in the opcode for, I'm going to get this address from the memory. This will be your address, right? And put the value in the destination. I want to get this address from some register plus immediate, put it in destination. I want to jump from this location to that location in my code, or I want to jump to the destination here based on certain operation. Jump if source 1 equals source 2 to this destination, something like that, right? Basically something like jump if source 1 equal source 2. If this is true, jump to destination. Otherwise, go to the next line. Right? I can do this. It's totally okay if I do this. So let's assume the opcode for an add is 0000011. And the load immediate is 11111. I can assume this, right? And I say opcode for a branch if less than is 00001. I can assume this. So from this toy ISA, if opcode for an add is 0000011, how do I represent the instruction add R0, R1, R2? Give me the bits. All right, so I'll give you 3 minutes. Write the answer on our chat. How do I do add R0, R1, and R2? So source 1 is R0, source 2 is R1, and destination is R2. So what's the opcode for an add? The opcode for an add is 0, 0, 0, 0, 0, 1, 1, right?
Yes.
Then how do I represent R0? 0, 0,
0,
0,
0, 0.
And then source 1 is R1, so it's 0, 0, 1.
Yep.
Source 2 is R2, so that's 0, 1, 0. That's all.
Yep.
Right? So if I see this bit pattern, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0, this is essentially add R0, R1, and R2. All right? It's as simple as that. It's as simple as that. So your first lab is just doing this. You just compare that to the manual for each instruction. Look at the binary, look at the bits, so you know the opcode. Just then you know the instruction, so you just do add, multiply, or whatever based on the opcode for the instruction that we have here, right? So at minimum, let's make sure for the lab, for the purpose of the lab, let's make sure you can do the add, subtract, multiply, those compute operation, load operation, and store operation. All right. And then the jump and branch operation, please make sure you try. Please make sure you try. But I'm going to weight that a little bit less for the first lab, for your first lab. So your first lab. The part that deal with compute operation, that would have the weight 60%, the load store. This would be weight 30%, and the branch, the rest of the 10% of the lab assignment. So that would be the breakdown, right? Make sure you have the compute up and running, then try the load and store, then the branch. Because the compute instruction is the easiest. You should get that quickly. It just compare the manual and look at the bits and run, right? Then you do load and store, and then you do the branch. Once you finish the compute and load storage, actually should be pretty simple. So let's go with our example. Let's do an add R0, R1, and R2. This is what happened. Unless that this line is at address 10. The program counter is at address 10. So you put it here, address 10, let's say it's right here. What are we gonna see here? What is the binary that we're gonna see at address 10? That represent add R0, R1, and R2 inside the main memory. We're gonna see what we just did, right? 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. This is add R0, R1, R2. You actually see those bits in the main memory. When you put address for that line, you will actually see those bits in the main memory. So that bit pattern, those 16 bits would be moved here. 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 0. It would actually move through this line to your decoder. Now your decoder would first figure out, okay, the first 7 bits is 0, 0, 0, 0, 0, 1, 1. That's an add. I know that register source 1 is from R0. Source 2 is from R1. So it would say, hey, register file, get this data from me. Get the data for R0 and get the data for R1. So the one that goes into the adder right here would be R0 and R1's data. And once you finish adding, what comes out would be R0 plus R1. Are you with me so far?
Yeah.
Basically, you would select the correct register file. This is my bad. Select the correct register from your register file. Register file is a collection of registers that you can pick from. So you pick R0 and you pick R1, put that into the adder, add them together. And then over here, R0 plus R1 would come in here, right? R0 plus R1, and you make sure you select In this case, now when you store it back, you select R0, R2, because you want to write the result back to R2. That's all. That's all when we have to finish that add instruction. What did I forget? I need to do one more thing. And if I don't do this, the next cycle, I'll do the same instruction. So what I forgot is increment program counter so that I can go to the next line, right? That's it. Again, that is your lab 1. Make sure you do this. At the end, don't forget you need to increment PC, so you go to the next line. Once you have to deal with the jump or branch instruction, your PC would take in whatever based on that jump instruction. It can be a register value. You go to somewhere else in your code, or you go to the next 10 line or something like that. So now I talk about the add instruction. Let's do another instruction. Let's do a load. A load means that I want to do something like this. I want to take a value in a DRAM, put it in my register. That's a load, right? I load something from the main memory. So let's do another instruction that do a load. So this is your PC program counter. Go in here. It's the address that represents the load instruction. Over here will be a load instruction, right? Then the instruction comes to the decoder. Decoder say, oh, okay, it's not an add anymore. It's a load instruction. If let's say it's a load immediate, right? Load address 20 to R7. Let's say I want to load 20 to R7. This means that I'm not going to do anything here because there's no need for me to do anything here. What is the address I put in here? Basically, from the decoder, say, hey, I just want to load address 20. So I just forward 20 right away, right? That's my immediate. I forward this directly to the address. So this has the value 20. I don't do anything with the adder multiplier. I just forward them directly to the address. And whatever data comes back, I then select 7 here so I can write the data back to the register file, right? That's another thing you can do with load instruction. So let's erase everything and do another load instruction that is load address at 10 plus R1 to R7. So basically this is load R7 equals the value at the address R1 plus 10, right? So I do R1 plus 10, that becomes my address. Over here, I just need to make sure this becomes R1 plus 10. How do I do that? Immediate becomes 10 because I want to add 10 to that. Then I select R1 so that the value of R1 comes out here. So this is R1 and 10. So this add results in R1 plus 10, right? That's it. Then I will have the data come back here and then I select R7. So I select R7 at the end. That's all. And then don't forget to include PC plus 4 at the end. All right, so that is simple. That is simple. And that is basically, again, single cycle architecture. Simple. We will see how simple it is in lab 1, to be honest. Once you know what each component are in the starter code, it's actually really simple. You just need to break it down. So how about branching, right? How about branching? So let's say if we want to do jump to address 24. I want to jump to address 24. Instruction come in, it turns out to be jump 24, right? 24 is the immediate. We're not doing anything with this. We just pass it through. So 24 comes out here. Goes in here and go directly to here because we're not really writing 24 back to any register. We just want to forward that to our PC. So this take the value 24 and that's all. is update the PC with the jump target. Then you go to 24. Next cycle is to make sure now IR take 24, so you know exactly there. Okay, that next cycle I go to 24. That's all, right? So again, so let me wrap up today's class. We talk about single cycle processor, and in single cycle processor, every single control signal will be generated to the data path at the same cycle. So everything happened in one cycle. So you need to select the correct thing. So if I go back to here, everything has to be done in one cycle. You would just make sure, okay, I'm going to forward immediate to here. I'm going to put the address right here. I'm going to select R0. I'm going to select R1. Everything will happen in that one cycle, right? So this is to make sure that our processor is correct. D1 would transform to D1 prime in the next cycle. In the multi-cycle processor, you only have to kind of assert the control signal for the next cycle, just for that part that you're doing. And we'll talk about this in the next lecture. Don't worry about that, on how to do this. So the benefit here is it decouples the latency of the control signal and the data path. It basically decouples how slow the memory is to how slow the multiplier is. It basically now it's a different thing. You put apart each of these components, so you are not tied to the slowest instruction anymore. That's the key takeaway. In multi-cycle processor, you are now not tied to the slowest instruction when you have to determine the clock cycle. We'll go into more detail later. So before we leave today, any questions about the projects? So first of all, you have a choice of, so once we are done with lab number 3, right, one thing you can do is, okay, that becomes your base infrastructure, and then you implement something we learned from this class that is not asked, something like a main memory or things like that. Or you can, also this is the default project that you can do, extend your lab code from lab 3 to support things like better caching policy, better branch prediction, multi-core or main memory, right? And then the lab 1, right? You are going to write a simple MIPS simulator that do single cycle architecture. Support the common instruction, not all of them, just a few that would make sure it runs. Now you have a functional simulator that runs Morse code if you write it using those instructions. And this is a lab that I borrow when we make this lab together when I was a TA at CMU. 18447 was the code for computer architecture class. Please keep in mind that you're gonna use this code for the future lab. Make sure it works and make sure it's neatly written, because you pipeline this for lab 2. Basically, we'll make this faster for lab 2. I'll skip this for now because I forgot to enable the submission. So let's skip this for now. We'll talk about this next week, but be prepared for me to ask. If you read the paper, if someone submits, I'll ask, like, okay, anything that you like and anything that you do not like. And these are your opinion. Just say it out loud. Don't worry, I'm not judging you. I just want the discussion. So typically, whenever someone submits a review, I'll try to have a discussion. This is to emulate. Basically, I'm not doing this for the purpose of I guess learning the material, but I want to emulate like more like a scientific discussion when you have to discuss the design, when you have to discuss things you read amongst your peers, among your friends, so that if you go to your lab or your each of the your potential advisors lab, right, and you talk to your advisor, talk to the other students, you can start to have a discussion for, it can be for your projects, it can be things you learn that you find interesting. It's just chatting, basically, right? And also, I want to learn about any topics that you might want to learn about, so I can prepare them. We're gonna have likely that we're gonna have like a few more empty slots at the end. So I want to kind of cater this for the benefit of your interest. As of now, I'm likely to talk more about the multi-threading, multi-programming, because Muhammad expressed the interest. And sorry, my cat is going crazy. behind me. And that's it for the class today. I'm gonna transition to a Q&A. So any questions? So let me actually save the annotation here. So let me stop. First of all, stop the recording so I can post the video.